What is up, car and tech fans? Today, we're going to put aside the creative gauge stuff that we've been doing and we're going to delve in to the dark arts. CANBus sniffing. Now, I've never done this. I understand that it can be incredibly problematic, but I've purchased some things that hopefully are going to make it a bit easier. Unlike the previous parts of this series where I showed you through the things that I've already done, I'm going into this completely blind and we'll be discovering how to do it together. I've never done this. I've not looked at any of the code, don't know anything to do with any of the services or libraries. I'm diving into it completely blind, other than the fact I've pre-bought a special shield, which we need in order to hopefully do this easily. I don't know. I've no idea what it's going to be like. So without further ado, let's get into it and I'll show you what I bought to empower this. And it's the CANBus Shield created by fellow parts electronic automotive YouTuber Mr. DIY. And here it is. A bunch of stuff that's made its way all the way over from Canada right to my workshop. Okay, so we've obviously got an ODB2 port adapter. This runs on the standard 16 pins, and this is just going to connect into this, which is the cool bit. This is the shield. I'm not going to go through all of these components. Basically, it's got a bunch of components which allow us to control things like read-write and whether or not we're actually able to write to the CANBus, as well as a bunch of buck converters, step-down modulators, and all that kind of stuff, so that this can sit very happily in the car and be powered by the CANBus without blowing up. And we've got these two 15-pin adapters, and that's it. That's the thing that you buy. You can get it from his store here. Like I said, it's store.mrdiy.ca. It was $40. And yeah, like I said, this is the stuff you get. There's a bunch of information about it. So the max data rates, the protocols it uses, pins it uses, blah, 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 blah. We've got the full schematic diagram. So if you wanted to build your own shield, we have the schematic for it. The big thing that we needed to note that this didn't come with was the ESP32, and it needs to be a specific one. As it says here, it's only compatible with the 30-pin ESP32 dev kit V1, which is different to the ones I usually use. Fortunately, shops exist. And that's it. There's a ESP32 Room 32, not a D or anything like that. This is the version 1, as we can see, dev kit V1. So this will all go together, that this mounts on the back of this, that way up. And then these will go in the sides, and then the ESP32 sits on the back. So you've still got access to these switches and components and things if you need to. One other bit that we're going to need to do is there's an enclosure for a free STL. So download the free STL. Download STL CAD files, yes please. So yeah, that's the enclosure. Looks like it's got like a print in place switch on the bottom, which will be used for pressing something. I'm sure there's a switch. Yeah, there's a reset switch in the middle of the shield, so that'll be the reset switch button. Probably stuff for heat ventilation here, USB port slots, blah 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 blah. So I'm not going to worry about going through that bit. I'm just going to get that printed in ABS. So when we're further down the line with this, we can use that. Before I dig into this code, because I think I'm going to be opening a can of worms. I'm not quite sure what to expect. I'm going to get the soldering done and get that out of the way. So let's quickly do that first. There we go. I believe that's basically good to go, other than the enclosure, obviously. So now that we've got this all soldered and hopefully nice and secure, we can get into the coding side a bit. And like I said, I've not done this yet. I don't know how this is going to work. I'm going to figure it out as we go through this video. But just looking at the documentation for the CAN Shield, we need these two libraries. So this one, ESP32 CAN, and this has a dependency on this CAN common. So I've just skipped ahead a slight bit and put the ESP32 CAN and the CAN common. I just downloaded them and put them into my Arduino libraries. So they should be good to go. Right, so what does this thing say? We've got the sample code. So let's just start with this. I'm just going to take the raw and just pop it in here, and then we'll take a look through it here. So Shields 1.3 or later use D4 and D5. So that's what we're using. Shields 1. We're using Shield 1.3b. So let's just see what this thing does. We begin the serial, print out some stuff, set the CANBus pins to these two. I presume that's input and output. It's the same as like doing a serial connection where you'll have upload and download. I think that's what that is. It's rate 500 kilobits per second, which is standard CANBus. Even though I've not looked into this code, I've done a little bit of research into like the formats that CANBus does. I think I remember 500 kilobits being one of like the standard ones. And we just set up this message, and it's got the ID, the length, and then the message, which is of variable length. Let's just try compiling this and just make sure that those plugins are working all okay and we're not going to get any errors. And if so, then what we need to do is add ESPNow into this, because of a problem that's going to hit us straight away. I don't use a laptop, so getting to see the output from here is going to be tricky. I might have to steal my partner's laptop in order to do this, because otherwise, yeah, I can't actually read the information unless I create the ESP sender immediately. And because the car's out on the drive, I can then send the message into a receiver up here in my office. That's probably actually not too bad. Let's do that, because then I can just leave the car on the drive sending information, and I can be up here talking to you in the warm and the light. So we'll put the ESP sender around this, and we're just going to, for now, send all the CANBus data. What we're actually going to want to do is in this loop, and where this message comes through, is probably filter it out based on the IDs. As far as I understand about CANBus, is the ID identifies certain things around the car. And there are some that are standard. So I'm hoping that I'll be able to just use that and very quickly get to the data that I want. But we need to, identify the IDs and then filter out and just send the information that we want, so we're not overloading the receivers. So let's just quickly throw ESPNow into this. It's pretty trivial. Just the only thing is making sure that we break this message down into bytes and send that string through easily. But yeah, let's create this as a full ESP sending device. We don't need another video of me writing default ESPNow code and a very simple structure in order to send to a receiver. We've seen that on a bunch of other videos. Here's me looking confused whilst some of this didn't work, but really it was just because I kept getting the MAC address wrong like an idiot. But all we did was create an object to hold our data of the ID, the length, and then the data packet itself, and then set up the receiver on a standard ESP32 dev board that I had kicking about that would receive that and print it out. So I could put one in the car to send stuff and have one in my house to receive it, so I could look at the serial output. That's it. How you doing down there, Andy? You all right? He's probably not all right. So this is the receiver. I've just called it CANBus receiver test. And it's very simple. It just has that same structure that we've got in our sender. It listens for incoming data being sent from ESPNow, and it copies that incoming data to this structure that we've created, an object of CANReceived, and sets new data to true. So we've got this flag, which maybe should be volatile. So we're going to set that to true. That's all it does. So copy and set to true. Like I've said in many previous videos, we try not to do anything in that serial callback function because it's too easy for it to get overloaded and potentially hang your application. Instead, we put this thing in the loop. If new data is true, then we do what we want to do and then reset the flag back to false again. So all we're doing is like setting up. This is just a setup for ESPNow. We don't need to dig into that. But if new data has been set to true, so we've been sent some more stuff, we're just going to print out what we've got. So the ID in a hex format, the length, and then trawling through the data one bit at a time. So now if I upload the code to here, in theory, it should be ready to start receiving information from my CANBus sender, assuming that the CANBus sender correctly gets information from the car. So I'm going to stick this by the window, go and plug this in outside and see if it'll broadcast over that distance correctly. This is a two-person operation, so I'm going to swap out for my glamorous and beautiful assistant. In your pot. Right, walkie-talkie. I'm going to be outside and I'm going to talk to you and we need to see if anything appears in this monitor. All right?
Roger, roger. I'll be back in a minute. Okay, it is plugged in. I am just turning on the car now. It hasn't blown up, so that's good. Do you see anything on that display?
No, not the blank bit under it.
Okay, it might just take a moment. I'm not sure. I'm going to try starting the car. I shouldn't need to start the car up. It should just do it. There's a chance I'm too far away. Okay, I'm going to try a different car that's a little bit closer and see if the other car sends some information up. If so, I might need to just change the cars around. Okay, I'm in and I'm apparently broadcasting. I don't know.
Can't see anything yet.
Okay. I appreciate you doing that. Don't worry about it. You are relinquished from duty.
Well, that was decidedly unsuccessful. I think I can't rely on it broadcasting over the distance into a house from outside of a house. So what we'll actually do is update the sniffer. Well, we don't need to update the sniffer because it already is going to serial print everything. So I just need to get Arduino IDE up and running on my partner's laptop because I don't run on a laptop. And then I'll actually be able to go out into the car and we'll do everything out in the car directly connected to the CANBus sender, just because we don't even know at this point in time if the CANBus sender is doing anything. The only way we'll be able to know for sure is to directly connect to it. So we'll do that next, but it's 7 o'clock in the evening. It's dark. It's raining. I'm hungry. I'm not going to do that today. We'll continue with this tomorrow when it's light and fresh and hopefully not raining. It's the morning, bright and early. And I didn't sleep very well, just trying to figure this out with my brain. So I decided before launching in with the laptop, let's just try to figure out really simply if we're getting a connection by using the onboard LEDs that come with the bus shield. So what I've done is add a little bit of code in here. So we've got two LED pins that come on the shield. So they're pins 26 and 27. So I've just called them here pin 1 and 2. I've disabled everything to do with ESPNow. We've just set them as output pins, set them as low, and then I've put debugging mode on for this, and then I'm going to write one of them, the green light, high if this initialization happens, and then it's going to try and read, and if I get anything, if I get any message, we'll set the blue pin to high. So yeah, green to know that it's come on and is the library is initialized properly, and then blue to know that we're getting any kind of message. So I just uploaded that code, and green light is on to show that it is initializing properly. So let's go put this in the car and see what it does. Okay, so ignore the mess. I've just been on a farm. Plug the ODB2 in down here. Okay, it's gone green. You wouldn't expect blue until you put the key in and go to power on. No blue pin, just green. All right, there is potentially another simple solution. Some cars reverse the high and the low pin in the CANBus. So when you do your initialization here, you need to switch around pin 4 and 5. At this point, this is a Hail Mary, but I'm going to try this, put it in, and then we'll see if this one works. This is just the debugging process that you have to go through with doing something new like this. Take 2. Holy, whoa. We have a blue light. It's received some form of data. Damn, maybe it's as simple as that. I need the laptop in order to just plug it in and see if it's putting anything out into the serial. Ooh, exciting. Laptop on the seat. This must be what it's like to have a Honda. Put this thing back in. And then, moment of truth. Is this going to reply anything? Ugh, bloody doors. Oh my god. I'm getting CANBus readings. Ignore the beeping, sorry. Great. It was just that the pins were backwards. Yes. Fantastic. So yeah, it appears like the problem all along was just that the high and the low pins were flipped. That does happen in some cars, and it's a known like simple fix, and fortunate that that's what it is. So this is all working, it seems, as we want. What we want to do though is make sure that we're just extracting the information that we really want. And fortunately, ODB2 has a standard, and a lot of the pin numbers are kind of common across a variety of different cars. And there are various resources where you can see these like IDs. Here's one of them by CSS Electronics. And this is the ODB2 PID table. So what this is, it'll show you the number in decimal, which is, you know, your normal numbers, and then your hex base, and this is what they will come up as. So if we take a look at the results that were coming out, they're all in this kind of format. So what it tends to do is has the most important things and the common things in your car that as the lowest numbers, and then they get a bit more obscure as you come down. So, you know, at the top, we've got system statuses, engine load percentages, and a couple we're going to want here, engine speed and vehicle speed. We're definitely going to want those two. And then a bunch of this like other stuff. And as you see, as you get to the bottom, you get more and more obscure. But we're going to want, let's just start with getting the RPM and the vehicle speed. So these two, OC and OD, which is hex 12 and hex 13. Now, I've just been doing some reading on it, and what we can just do is with this, we don't need debugging mode in here anymore. This watch for here, CAN0 watch for, you can tell it the PIDs that you want to look out for. So we want to look out for 00C, so that's 12. And we also want to watch out for 13. So we would just want to look out for those two IDs to start with. So if we take this, go back into the car, and then start it up, we'd hopefully see one of them displaying a constant number, because it's not going to be changing because the car's going to be static on the drive, so the speed will be 0, and hopefully you'll see all zeros in that output. And then as we like tap the RPM, we should see those values come up and down. Right, so it's currently in and connected, but this trying to read is happening faster than I can refresh it because we've got rid of that delay. Let's see what happens when I put the key in. It should do nothing because those two IDs I don't think will come through. Yeah, okay, it's still, the light is just green. but when I turn it on, what is happening? Am I getting anything? No. Maybe those IDs need to be decimal, not hex. Maybe the IDs are a different format in this car. It could be one of many different problems. What I need to do is just display everything and then figure it out from there, because we're clearly not filtering the IDs now properly. But it's fine. This is a process. This is what we have to do. Right. Let's try that again. I'll make sure I'm sticking to the bottom. There we go. Yes, right, okay. Oh, we've got a load of data coming in, but this is fine. There's going to be way too much to understand and read. But when I start the car, the idea is now, amongst all of this data, is the data I want. So I'm just going to let it run for a second, then maybe tap the accelerator a few times. There we go. So now I can just stop. And I'm going to need to disconnect the board to stop all that chaos. And now we're going to need to go and just trawl through that data to see if we can pick up the correct IDs and filter that down. So that's going to be fun. Oh, there's some that are running a lot. We'll see. Let's take it back inside. I was thinking that maybe I could just trawl through the data and identify some patterns. But in that short blast in the car, I have 141 pages of data. And although I can definitely identify a few things, there's some repeat patterns, there's definitely some things that are sat at 0 all the time. It's difficult to understand what is what. So I'm going to actually have to do something I didn't think I was going to have to do, which is use something like SavvyCan, which is a CANBus data parser, to show the data in a way that I can actually understand what's going on and start to pick out the IDs of the things we need. You see, the problem we have when trying to analyze that much data is, how do you pick out one static thing from another? We have the car just sat on the drive, so the speed isn't going up and down, and there's lots of other things that are fluctuating all the time. So how do we pick out speed and RPM? So we're going for a quick drive, and we're going to drive in a pattern. So what I'm going to do is get the car slow, driving along at a slow speed, then we're going to quickly increase speed, hold it there for a second, put the clutch down, hit the accelerator a few times to spike the RPM, and then quickly slow down, which will give us a pattern we can look for then on a graph. So I'm just driving along at the moment at 20. I'm going to go around this corner, slow down. So we're going to go to nice slow speed. Up to speed. And then slow down. Okay, and then I need to unplug it, which stops it recording, because otherwise I get way too much data available there. And then that should hopefully mean I've got a few seconds of data that I can look for that pattern when I open it back up on the screen. This is a painful process, but what I've ended up doing is extrapolating all of that data that was in the serial log. Not the ideal way of doing that. Usually you would hook up your CANBus sniffer or your something like SavvyCan up to the ODB2 and just read it as you're driving around or whatever. But because I can't do it whilst I'm driving around, we've had to extract the data from the serial and bring it in. But we've got basically this big old log of stuff. So what it is a timestamp, the ID of the hex ID of the value that's being sent through, the length of the bytes, and then the bytes themselves. So what I'm able to do with this is drop it into this application, which is called SavvyCan. And what SavvyCAN does is then allow us to visualize this data in a bunch of different ways. And the one is best, I find, is flow view. So if we just take a peek at this, this is all the data we've got to play with. And these are all of our different IDs. And you can see with the graph, some of them do different things. So these ones, you know, straight lines, don't really have to worry about anything. It's not really showing as much, and we'll show the full chart. So this is something that goes up and down a lot. A lot of these are just static. Some of these will be something that switches on and off. This might be an indicator or a light, or, you know, there's lots of things that could be. But when we start to go down, we start to find some like this one that's got a smooth up and down here. And then if we go down this list, there's another couple here. This one's got some kind of smooth, and if obviously it's a bit chaotic to read, so we can start to remove some of them. The red one's not got a lot of relevant data, purple one hasn't, blue one sort of, grey one hasn't, yellow one just kind of smooths along with everything else. So, you know, you can start to look at this, like this could easily be the 3 RPM blips here. So where it's going off the bottom and off the top, it could be that this bit here actually sits on top and there's an adjuster. So one of these other bits. So this blue one, if the blue one is 0, is 1. Basically, long story short, I'm not sure where RPM is yet. I've got to find it. It's one of these, or it could be that one there, that red one. But 721 here, this is the speed. And I've played with this enough now that I can verify that this is the speed, because I've been on this for several hours since we went out and drove. But yeah, I couldn't show you me sitting here with my head in my hands for a lot of it. So what we've discovered is if we remove all of these except for those 2 bytes. Now, this, as you can see, goes along and jumps to the bottom and goes up and then down to the bottom and up. And the reason it does this jump is where it's here, it should continue up to here and then come down and then continue down here. But it doesn't know to do that by itself, because each one of these bytes is within a range, and that range is 0 to 255. It's the maximum number a single byte can be represented as. But if we look at this next one, this grey line at the bottom, it steps up 1 here, and then steps up again here, which is basically the flag that's saying it's actually another level up. 2 bytes that we're interested in are 1 and 2, and 2 is actually the 4 bytes before 1, and it's called a big endian. So 1 is a byte, 2 is a byte, but 2 is actually the byte before 1 when you join them together. What that means is the code has been adjusted like this. So just for now, everything is the same, except where we come into our loop, we can now read the CANBus message. And if that message ID is 721, which is the message we've just identified, 721, we're going to extract byte 1 and byte 2. So byte 1 will be the second byte, and byte 2 will be the third byte. But the big endian, we need to shift byte 2 8 to the left. When I got out testing it, the number was way too big. It was like I was driving at 25 miles an hour and it was showing about 400, which makes me believe that it's coming through in kilometers an hour. So 28 miles an hour is about 40 miles an hour. So it's probably got to convert from kilometers an hour to miles an hour and then divide by 10. So I actually haven't divided it by 10, and I should probably divide it by 10 before I convert it to an integer, just to keep it better. So what that means now is the big endian value is coming through about 500. So we divide it times by 0.6, this is the number of miles per hour to kilometers per hour. So bring it down from 500 down to mid 300s, and we divide it by 10 in order to get our miles an hour as a float value, and then we convert that to an int to get the closest int, because we're only displaying ints on our little screen. So in practice, this should mean that when I drive now, we get a nice display that shows miles an hour, even if only on the serial print. So that seems to have taken care of miles an hour, but this is the process of CAN sniffing, and everyone says it's painful, and they are right. So I'm going to find the RPM, and then I'm going to hook up the gauges, but it's 11 o'clock in the evening now, and I'm not going out to drive in the car. Now at night, it's all frosty out, so it's not worth it. I'll go again tomorrow, check with the serial monitor to make sure that the values are about right, and then we'll connect it up with ESPNow to the gauge, which should be pretty trivial. Fun. It's not fun. It is. It's rewarding, but it's not fun. I didn't stop. I kept going like a little gremlin. And I found something interesting. I think I found it. I was looking through some of the other formats, and this one struck me as a potential. It looks like it goes up here, and then we've got like the gray again as the flag to go up to another level. And then it looks like it's got like a big rise, because we did that. And then I let off, and then I did the bow, 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 3 spikes of the accelerator while the clutch was down. So it needs to spike, but the speed not actually go up. The speed will have been coming down at that point in time. So plotting this properly can be a little bit of a pain, but some AIs can do it for you really well. And there are a bunch of them where you can give it basically your entire CSV or text file full of data, tell it what you want, and it'll extract it and graph it for you. One such AI is Julius, which I've just been using for this. So I uploaded my text file with all of the data in, told it want to get the speed and RPM from the CANBus, and it suggested some ones that it might be based on some of these graphs. And then I said, let's basically, I started to narrow it down to endians and using endians as adjustment points, which got us closer and closer until I got to here, which was the speed one. Say that, yeah, using bytes 2 and 3, and it should have actually been 1 and 2. When we got to bytes 1 and 2 with the endian adjustment, this is the graph that it gave me, and this looked good for the speed. So this was, a pretty clear sign that the speed was probably right. I tried another one that looked promising, and the graph came out like, this is a lot of stuff that I've been doing with this, like that. Not so promising. But then I found that one I just looked at, 561, and it looks like this. So, you know, putting your foot down, and then the big acceleration push, and then the 3 spikes, which is something that I was, looking for, those 3 spikes. So I just copied that graph and copied the speed graph, put them together in Photoshop, and this is what they look like together. So this looks pretty promising, that the blue line is the speed, and this one is this is where I popped the accelerator a few times as it was. See, I'm slowing down, but you still got those 3 notable spikes. So we'll come back to this tomorrow again, day 3. I thought this was going to be quick. Okay, day 3. Let's finish this thing. I don't think it's actually going to take too much work. What I've done is captured that second ID. So we've already got the one here that turns out it's speed. I thought it was going to be RPM, but it's actually speed. So we've got that, we've converted that, we've done all that. So what I've done is take like I said before, with this first and second byte in order to switch them for the most and least significant byte. We've got 3 and 4, which I've identified, produces this graph. And by the looks of things, my RPM number was maxing out here around 1600. So I've got a feeling when I spiked it, I probably spiked it close to 5,500, 6,000. I don't know. I didn't look what number I spiked it to. So I've got a feeling the scaling factor for this is around 4 times. Every car's RPM value has a scaling factor. So it translates what the number that comes in from the CANBus is to the actual real world number. I've got a feeling mine's in the range of 4. So what I've done is taken that calculated big endian value and times it by 4 in order to give me an RPM integer, which we're just then going to print out. I think it's probably going to need tuning again. So what we want to do is let the car sit at idle and then just view where it is, and then we'll see where it is on my gauges and then see how that compares to the value that's being printed out. And then maybe adjust that scaling factor accordingly. And once we've got that factor and this factor, and we've confirmed that they're all okay, we just need to turn on this sending stuff, and we're basically going to be good to go. So let's go get some numbers and then hook up everything to the gauge, because I don't think this is going to take very long at all. So I've just started it, a cold start on a cold morning. It is brisk, and my rev counter is currently sat at 1,400 and dropping. So I'm just going to wait a few minutes until it's idling at a steady value and not continuing to go down. It'll be when it reaches about 800. I'll give the rev a couple of taps, just to help it settle. So now that it's sitting at a constant value and it's not expected to change much, let's plug in mine and see what value it's currently coming out with. Is it in the right ballpark? There we go. Okay, so it's running a little on the high side, 1,050. Just out of curiosity, I'm going to raise the RPM in front of me to 2,000, and then we'll take another look at this. So I'm just going to raise it carefully and slowly to 2,000. Let's go, keep going a little bit more. Okay, that's 2,000, and that is showing 2,300. So it's definitely high. I'm just saying these numbers out loud so I can refer to this video when I need to do the maths. I'm going to go one more to 3,000. It's 3,000. That's saying 3,500. So it's definitely on the high side. Let's do 4,000. Sync maybe. And that's 4,700. So it's definitely high. Okay, so it seems to be out by a scale of like almost 20%. So we can use those numbers to calculate what factor we should actually be multiplying by. Now we need to do the exact same thing with speedo and see if the speed relates to the driving speed. So in order to do that, let's go on a little trip. So we're just going to go onto a straight bit of road near me that's unlikely to have any people on it this time of a Friday morning. Okay, whatever. I'm running at 22 miles an hour on the speedo there, and it's showing 21 on my digital one. And I know that speedo that is showing in front of me is about 1 mile an hour over at 30, according to the GPS. Though it's actually, my GPS is showing 22 as well, so 21, 21, 22. They're all basically right. I do need to try it at some higher speeds though, so there's a motorway a few minutes away, so we'll just head there and then I can test it at 70. Okay, so the 40 mile an hour restriction is coming to an end. Of course there's a Nissan Qashqai right on my ass. We're going to increase to 70 in a second, and then we'll check what that's all about. So let's go. Funny English drive. Wrong straight bit. Okay, 70 on the GPS, 69 on the. Looking at this. So I think we've simply got a rounding error here. Maybe I should have left the full number in as opposed to trimming it to an integer before testing this, but it seems like, yeah, we're in basically the exact right ballpark. So let's just try changing that. So converting to the closest value as opposed to just rounding down. Then we'll adjust that ratio. And we'll bring it up. Yes, I best head home. According to my video, when it was at 2000 RPM, it was showing 2250. When it was at 3000, it showed 3.5, and when it was at 4000, it showed 4700. So let's bring ChatGPT into the situation. We all know it. I am currently multiplying a number by 4, and it's showing me the values 2250 to 3500 and 4700 when I want it to show 2000, 3000 and 4000. What number should I be multiplying by in order to be closer to these values? Find a best average. I expect what this is going to do is compare each of them and find the ratio of each of them. So each one will have a ratio of like 0.8 something. And then hopefully find the average of the three and see where that gets us. There you go, compute ratios. Ratio 1, ratio 2, ratio 3. Dun, dun, dun. Exactly what I thought was going to happen here. 0.86. So 3.46 instead of 4. 3.463 instead of 4. Great. So 3.463. Thank you, ChatGPT. That's likely to end up as a float value, so I just want to make sure I cast to an int. Otherwise, I'm going to try and be passing an RPM of like 1850.753, and it's going to break everything. I know we declare this isn't in here, but let's just redo it, make sure everything's groovy, and just make sure all that compiles. And just make sure this is still relevant. So this will need changing. So we need to just do an adjustment of what this message looks like here. So we're not going to do any of this anymore. We're going to send an int 8 of miles per hour and an int 16 should cover it. That'll take us to 36,000 int 16 of RPM. And that's all I actually need to save and send in between the two. So there's got this new structure and this new CAN message. So what we just do is when this happens, we make that new miles an hour and we set CAN message dot miles per hour equals 2 miles per hour int. That's that one set, and then the other one sets in here. RPM is RPM int. So then don't need any of that. Don't need any of that. We can just send that CAN message to the receiver. I do need to do some adjustments on the other end of the speedo in order to receive this thing, because the structure is going to be slightly different now. Also, we're not going to rely on this satellites anymore. So that icon I was using to show whether or not there are satellites connected and whether or not we're connected to the GPS can be removed, because we're not going to be doing that anymore. So assuming that ESPNow can handle the rate that we're going to be sending things to it, this is effectively done. There might need to be a slowdown. If there is, I've got a feeling the bottleneck is going to be LVGL. What I have just done is remove the animation for now when the update of the RPM happens, so it'll just be really quick. But I've got a feeling the data comes through so fast it's not going to look spotty. I guess the only thing left to do is go and plug all this into the car, drive and see what it does. That seems okay, so I'm holding, let's hold 2000 RPM here. Two thousand. Oh boy, does the speed work as well? Oh, it is freaking out. It is probably getting too many requests. I'm going to have to slow it down. I believe the reason it's failing is that the CANBus is able to send out RPM and speed data at 25 millisecond intervals, so really, really quickly from the CANBus, which means that it's writing on ESPNow at 40 times a second, and the maximum draw rate, the maximum refresh rate of LVGL is 33 frames a second. So because we're pushing it beyond its capabilities, that's probably why it's flashing. So we'll just add a little bit of code in here, and we're going to add a task handle. So we've got this send speed interval, which we're going to limit. We're going to do the interval at 100 milliseconds. So what we're just going to do is have the loop here do exactly what it was doing before and just overwrite those messages into the local object, but then we're not actually going to send the object as part of that loop. Instead, when we do the setup, we'll create this task and do the send speed task. And that's going to just be the ESPNow send. So that's all this thing is going to do, and it's just going to be doing it every one of those intervals because we've got all the tick stuff in here already with the timers. So everything should work really well, and then this is just being done 10 times a second, which is easily within the capabilities of both ESPNow and LVGL. So with this done, effectively, I think that's it. Let's go for a final test drive. See the revs come up there, up to 3,000. 4. Ladies and gentlemen, I think we've done it. I think this is good. So this is saying 23, it's saying 21, 22. I mean, it's within a mile of hour of what my GPS says. I'm within one of what this one says, and I know this one's always ever so slightly over. So there, 25, 25, 25. Seems plenty responsive because it's updating 10 times a second. And if I dump the clutch and give it some revs, you see that revs perfectly high at the top. I think we've cracked it. I think this is good. Oh, great. It took 3 days of twiddling and poking and investigating and learning in order to get this going, but it's all going and it seems to work really nicely. No real changes I want to make it. I'm happy. That's good. That's done basically. The only things you might need to change if you're doing this is your CAN message IDs and the bytes. You're going to have to figure out where they are in your CANBus. Obviously, if you have a 350Z, you can do this and it'll work probably, so long as everything else is set up properly. And yeah, there we go. One more job ticked off. The dark art of CANBus sniffing sorted. Now I do need to delve deeper into it and start getting other values like door open or lights on or all these kind of things, because we're going to, at some point moving into next year, replace the entire driver's console with a full custom console. So we need to replace everything that comes out of the CANBus. We're talking obviously RPM and speed, but all of our levels for different things, all of our indicators, temperatures, everything. We're going to have to figure out all of them. So there's going to be a lot of time doing things like sat vCAN on a laptop next to me, turning lights on and off and seeing what values change. Yeah, there's going to be a whole load of that, and that's going to be a whole other video series after we've done these gauges. But I think that's an interesting little look at what it takes to, try CANBus sniffing for the first time. Actually, from a coding perspective, isn't too difficult. This code to get it running is super easy. So if you've got the time and the patience to dig into this data and do what I did, go for a drive in a pattern, like speed up, slow down, something you can spot on a graph, that'll make it a lot easier to find the data that you're after. But yeah, that's how I would go about it. That's how I did go about it. And now you've seen that despite never having done that before, we now have a gauge up and running using CANBus data, and it seems really good. So I'm very happy. We do have one more gauge in the series to go, which is subject to change. Somebody in the comments of one of my previous videos mentioned about a Spotify gauge had gone in their car with, displaying information about the song that's currently playing. And I do like that idea. So maybe we'll do that. Maybe we'll do one that shows levels of different temperatures and all that kind of stuff coming from the CANBus. Maybe we'll do both. I don't know. If you have a favorite that you'd prefer to see, stick it in the comments and let me know. And if one is overwhelmingly popular, then we'll do that one. And then when all three are done, we need to do the thing about how to mount them all into the car, 3D printing and modeling the mounting and enclosures that sit in the back of the existing center console. Plus, we need to think about power requirements, custom PCBs, the change of the enclosure for the CANBus senders, a bunch of subsidiary stuff that's going to happen before this is all working. But I don't think it's that far. I think sometime in January, this will all be working and up and running in the car, which is going to be awesome. I can't wait. That's it for this one. Hope you enjoyed it. If you do like this kind of content, make sure you give it a thumbs up so I know. And if you want to see more of this series or these kind of automotive Arduino projects, be sure to hit subscribe because we have lots coming, especially as we move into the new year. This is probably going to be my last one before Christmas. So have a wicked festive season, whatever you're up to, and we'll catch up with you probably in the new year. Have a wicked one, peeps. Take it easy. Bye-bye.